Okay, so I will explain the basic parent function equation of exponential function. Okay, so we see this equation, we consider this equation as the parent equation of exponential here. So if you have okay, this is parent function of exponential equation. And here, the A, as usual, indicates the leading coefficient, right? Then what's the big difference between, especially the exponential function equation in terms of the variable with all other functions are this. Usually we input any values into the function equation, but x variable is the base. But in this case, as you notice, this variable x is the exponent. Then, now, since the variable being exponent, we have to have the base here. Then we call this base b as exponential factor. Then another characteristics that we notice from exponential function equation is, think about the case the input is 0. Then, so if x is 0, then the y is whatever the a as a leading coefficient and whatever the exponential factor b raised to power of 0, and then this one gives you a times anything raised to power of 0 is 1, and then it becomes a, right? So that means when we talk about the real life examples of exponentially growing or decaying, then by the time the 0 second passed, is always happens to be the leading coefficient a. So this comes in very convenient position that we can utilize that leading coefficient a as the initial amount. So you will see that coefficient A will be original price that it will depreciate, or the principal that you invest to the account that gives you compounded interest rate, and so on, right? Okay. Then, yeah. Then this is the basic equation structure here. Then one examples that you see from the practice problem is talking about depreciation. If you buy a car, it's so and so amount, and as time goes by, every year, the price of your car will go lower and lower and lower. Then that's perfect example for us to look at the depreciation exponential models here. Then, what part of this basic exponential equation will be changed to model the depreciation model here? So from the structure, y equals leading coefficient a, or initial amount in this case, times the base b, or exponential factor b, raised to power of x. And consider the exponential factor b part indicates the rate that it gets increased exponentially or decreased exponentially here. then it's the same, but let's focus on depreciation for this time, okay? So then, if the b, the exponential factor b, can be written as this, 1 minus r, then r being rate. Then this means the original amount, and every time, whatever the time period that we check, then it exponentially depreciate, right? And then this will be the model for the depreciation here. Then it goes, y will be the initial amount, and now it will take the parenthesis and then raise the power of t. Then in this time, t means time. Then r means rate. Then one thing that you have to remember within this whole unit, and whenever we talk about the rate, and it could be given as a percentage, like 5% or 0.05%, or any type of the percentage. But when you calculate with given interest, in calculation, you always have to have the decimal format. You cannot use the actual values that goes with the percentage into the calculation at all, right? You always convert the percentage into the decimal. Then in this case, A will be the initial amount, and that's all we have here, right? Then what could be the exponential growth? So compared to this, instead of going down, instead of decreasing, if something is exponentially increasing by a certain rate, then it's gonna be this. So then this is exponential growth by the rate compared to the depreciation model here. Okay, then let's do quick examples. Then the depreciation is nothing but actually exponential decay by the rate, right? Okay, example. Let's go with the past sentence, past tense. If you bought a car soon you will do so. Buy a car. You bought a car for, let's say, $15,000. Then after 5 years, the price of your car became to be $8,900 only. Then what was the rate that every year it got decreased, right? So then in this case, we can utilize the depreciation model for finding the rate here, right? Okay, so then what is the amount after what is the price after 5 years? Here, 8,900. Then what was the original price that you just bought the car for the first time? And then it was 15,000. Then the depreciation factor is going to be 1 minus R. In how many years? 5 years. Then the first step that we have to solve this equation for the R here is we have to isolate the variable R. So first, we will divide everything by 15,000. Then you should have approximation 0.59 equals 333 forever. Then I have 1 minus R raised to power of 5, right? Then now, in order to get rid of the exponent there, the manipulation for us to do is we do raise both sides by exponent 1/5. That means we are putting fifth roots to both sides, right? So then either fifth roots or we can simply raise both sides to power of 1/5. Then when you use your calculator and remember you have to have the base raised to power of 1/5, any rational exponent, remember to use parentheses. Because if you don't do that, and then it's gonna be just raised to power of 1, which is the same, and just divide that by 5 only, right? Calculation. Nothing, tip. You need parentheses. Or I don't know if you guys have that NC1 90 something, you know, TI, then that could just do its work without worrying about the parentheses or what. But scientific calculator or just like mine, and you need a parenthesis there, right? Then you will have approximation of 0.900865071 and so on. And finally, we can get 1 minus r out. Then all you have to do is be careful with the negative sign and you subtract 1 from both sides. Subtract from both sides, right? Then it's gonna be r being 0.991349269 and so on. I just worked it out in advance. Then if you are supposed to answer in percentage, then do not forget to move the decimal to the right twice. Then it's 9.9%. Or if you can answer just rate by itself as a decimal form, and then you can just leave it as 0.099, and it must have the instruction in what place that you have to round up or etc. Okay, and any question? Okay, then we will move on. Compounded interest model. And in the UC Scout instruction video that the teacher explains the formula, and there's 2 examples already done there, so I would not really go deep, but we will have some notes in here, okay? Okay, the formula for the compounded interest is nothing but this. You invest P amount of the money at R% interest rate and compounded n times per year for T years. Then how much money will you have after T years? So typical compounded interest investment problem would look like this. Then in this case, color-coded parts on the formula, the exponential model, would go the amount after T years, the amount the principal, the initial amount that you start with, Then the rate part will be, so the exponential factor here is 1, indicating the original amount, the first time, before any time passes by, plus the rate, and then in this case, R should be the decimal form, not the exact value that you go with the percentage, right? Then over then the numbers of times, how many times it calculates, it gives the interest over the year, the per year. Then it also multiplies the number of years that it stays in the account. Right here. So then what you need to know for sure is the R is decimal in the calculation. And then now the N. So this N is divides the rate. And then this N is multiplies the number of years, because it's obvious. So it's not only happens once a year, then you have to divide the rate goes to your account evenly every time you add the compounded interest. And also, since you have more than one time giving the compounded interest happening over the year, and then you have a certain amount of time over several years, then the total numbers of total times that you get the interest is how many times it happens per year and how long, like how many years that happened. So that's why it multiplies on top. That goes with the time, right? Then this one is indicates the first time, like it's not before the time passes. Then this is the principal amount. This is the principal amount. And then what is this? This is the current amount. Okay. Then if you haven't, and go back to watch the UC Scout video, and there's a couple of problem solving there. So sometimes you are being asked about this situation, then how much will you have? Or just like we saw previous in an example, sometimes you are supposed to find the rate. Sometimes you have to find how long it takes to make the amount with a certain amount of the principal and how many times it gives over the year, okay? Then now we will move on to the continuously compounded interest rate problem. In order to explain that, and I just saw really interesting approach for that formula, and it looks like the principal and the base, the exponential factor is nothing but lowercase e. That's very special value, just like pi. And then we call it Euler's number because that number was found by the mathematician named Euler. Then we can see how that continuously compounded interest rate model developed. Okay, so we focus on the N. N is how many times happens over a year, right? Then you need to know how to interpret properly from the context written in the direction first, because you typically will read the context. It says the compounded interest annually or semi-annually or biannually or quarterly or monthly, weekly, daily, even hourly and minutely, and so on, right? So I will give you brief chart here. So with this model, let's see if we have the context. It says annually. That means it only happens once a year. So then let's take a example that, okay, go back. Okay, then example here, you invest $1 at 100% interest rate. Compounded. Something times per year. How much will you have after 1 year, right? So this is the situation. Then the reason why I have blank times per year, because we will see all different kinds of models, like annually, biannually, and so on, right? Okay, so then this rectangle here is the number 1 in annually. So that means we invested $1. So the model will go principal 1 and the formula 1 and plus 100% in decimal is 1, right? So it's 1 over 1 because it happens annually. It's 1. Annually, it's 1 time. Then for how many years? 1. Then the answer is 2. Right? 1 times 1 plus 1 over 1 is 2. 2 raised to the power of 1 is 2, so it's 1. Okay, then number 2. If it says semi annually or biannually, that means it's 2 times per year. And that means principal 1 and formula 1, and it's gonna be now 1 over 2. So because it's 2 times, and it's raised to power of 2 times 1. Remember, it has to multiply, so here, so it's n times for 1 year. And then if you calculate it, it's gonna be 1/4 as the factor. So it becomes 2.25. Okay, then and so on. Then the third one, it says quarterly. So you divide whole year into 4 even periods, then every 3 months, and then you will get the promised interest here, right? So then it's going to be 1 and 1 plus 1 over what? 4. And then it's going to be 4 times for 1 year. Then if you calculate it, it's going to give you 2.44140625. Okay, then we will do more. Then what about monthly? Monthly means the n becomes what? 12, because there's a 12 month per year. So number 4, monthly. That means principal $1, formula 1, and then 100% of rate over, now we get 12, and then raised to power of 12 times for 1 year. Then the approximation will be 2.61303529 and so on. Then let's do weekly. Do you know how many weeks that we have over the year? Who knows? There's 52 weeks, 52 weeks. Then 1, principal, 1 plus, it's 1 over 52, then raised to the power of 52 times happened over the year. Then it gives you about 2.692596954 and so on. Then let's do daily. How many days do we have per year? 365. If it's not a leap year, then it's 1 and 1 plus 1 over 365. Then it's going to be raised to power of 365 times 1, and approximation goes 2.714567482 and so on. And what about the hourly? Hourly will be 1 times 1 plus, so every day we have 24 hours. So if I'm too lazy to copy the numbers on the denominator, so it's simply, there's 365 days, but every day has a 24 hours. Then this is gonna be on top of there too. So 365 times 24 times 1. And the number goes 2.718126691 and so on. So let's see here. From 2, it happens once a year. And if it gets more times happening, oh yeah, 8,760 hours in a year. Oh my God, yeah, okay. So then it does make difference. It does make difference. So then we hypothetically think about the situation, like as we move on the over shorter period time that giving the compounded interest given, then it gets a little bit more, right? But between the once a year and then hourly, or we can just think about like minutely and even secondly and so on. But the numbers that you get, even shorter period amount of time, and then it's gonna be very similar, this 2.7 around. So hypothetically, if we think about it, every moment, even nanosecond, that there's one investment gives you the compounded interest continuously. There's no gap between the moment that you get the compounded interest. So that's why we do so continuously. That means, let's say we define X as a variable that goes infinitely many times, right? Then we can write the equation for this model is principal $1 in formula 1, and then how many times it happens? It's with 100% rate, then it makes infinitely many times. Then infinitely many times over the year. Then it becomes that special number, lowercase e, that we call it, it's Euler's number E. Then with this investigation, then we can have our model continuous growth, or especially the compounded interest model. You will get this amount of money with principal investigated, and the exponential factor is the lowercase e, the Euler's number, and raised to power of rate r times t. So this is continuous compounded interest model. Then the backstory related to how you can interpret context that given direction to solve this type of one here. I hope you guys found this one a little bit interesting. I thought it was very, very brilliant to explain everything behind, besides that you saw from the previous video and while you're taking the practice problem. So I checked all 10 problems and the practice problem, and then they are very similar, and it's just within these 3 types of models there. So I think you guys can do it if you haven't. But still, if you guys have any questions, and let me know by email, okay? Oh, you know what?